Alright, so the next one is exercise 21. Here n is an even integer greater than 2 and phi is an automorphism of the dihedral group Dn. We have to determine the phi image of the rotation R180. Okay, so let's see the solution. In the beginning of the solution itself, we are going to use the fact that n is even, and because of which the center of Dn consists of two elements. One of them, of course, is the identity R0 and the other one is R180. Since n is even, this is the center. Okay. Now, since R180 is a central element, phi of R180 is also a central element. Because phi is an automorphism of Dn, that's why R180 commutes with all the elements of Dn, so phi R180 also commutes with all the elements of Dn. So that means phi of R180 is either this or this. However, it cannot be this. But why? Since phi of R0 is equal to R0. This is also a property of any isomorphism, namely that any group isomorphism maps the identity element onto the identity element of the other group where the function is leading us. In this case, since the function is an automorphism, so that other group is Dn itself. So that's why phi of R0 is R0. And since phi has to be an isomorphism, so that means it's 1 to 1. So this cannot be R0, because otherwise two different elements R0 and R180 will have the same phi image, and that will violate the one-to-one-ness of phi. So this thing is R180 itself. So that is the solution. Next, 22. Let phi be an automorphism of a group G, some automorphism of some group G. Prove that the set H, which is the set of all elements X in G that are kept fixed by phi, that is phi does not change any of these elements. So we collect all those elements and that subset of G is called H. We have to prove that this is a subgroup of G. So it's a routine task, but anyway, let's go through it. So before we verify the definition, I didn't mean to say definition, but before we verify the conditions in the subgroup test on H, we have to make sure that H is non-empty, because the empty subset is never a subgroup. Since the phi image of the identity element in G is the identity element. This is a property of any isomorphism and hence an automorphism. So E belongs to H, and as a result H is non-empty. A purely notational remark: we often do not distinguish between the symbol for phi, the Greek letter phi, and the empty set, but actually they are not exactly the same thing. Phi is like this, whereas the symbol for the empty set is this. You write 0 and then strike it out. Okay, they are not the same. You can see this is more like a striked out upright ellipse, whereas this one is a horizontal ellipse. Okay, there is a slight difference. It's like this. Okay, so now H is non-empty, so now we can take two elements from H and then verify the usual stuff. Let A and B belong to H. Then the phi image of A is A and the phi image of B is B. So what is the phi image of AB? Since phi is an automorphism, first of all, this is phi A, phi B. But phi of A is A and phi of B is B. So AB is also unchanged under phi. Also, what is the phi image of A inverse? Since phi is an isomorphism, so this is the inverse of the phi image of A. This is also one of the properties of an isomorphism. But this thing is A itself, so it's the inverse of A. Phi of A is A, so A inverse. So AB as well as A inverse are unchanged under phi. Hence, AB and A inverse both belong to H. So by the subgroup test, thus H is a subgroup. Of G. So that is the solution. Next, 23. Give an example of a cyclic group of smallest order. of a cyclic group of smallest order which contains a subgroup isomorphic to Z12 and a subgroup isomorphic to Z10, 20. Yeah, instead of writing such a long sentence, let me write like this, which contains subgroups isomorphic to Z12 and Z20. Okay. No need to prove anything but explain your reasoning. So what is it that we have to do here? We have to search for a group which is a cyclic group in which you will find two subgroups. One of them is isomorphic to Z12 and the other one is isomorphic to Z20. And additionally, our cyclic group should have the minimum possible order satisfying these conditions. Let us first of all see that if we suppose that there is such a group, such a cyclic group, then what is the consequence of that? What is something that is necessary for this to happen? Let G be a cyclic group having subgroups isomorphic to Z12 and Z20. Let's give these subgroups names also. Such that H is isomorphic to, okay, I am using this symbol to denote the fact that these two groups are isomorphic. Okay, I don't exactly remember precisely what symbol is being used in this text. Okay, I have not seen that in detail. So by this I mean that these two groups are isomorphic to each other, and K is isomorphic to Z20. It may look like this, okay, I am not sure, but I am going to use these two tildes. Then a consequence of this is that they will have the same order and these two also will have the same order. Okay, now we know one fact about cyclic groups, namely that if we have, I should have additionally said this also, this be a finite cyclic group. Okay, we have to explicitly mention that because in general it may be an infinite cyclic group also. So this is a finite cyclic group which has subgroups isomorphic to these two groups. Now the fact that we know about finite cyclic groups is that the order of any of its subgroup has to divide the order of the group. This fact in general is true in not just for cyclic groups but for any groups, and it's known as Lagrange's theorem, but we will get to that. Okay, we haven't got it yet. For cyclic groups it is there. Then by that fact, order of H has to divide the order of G, and order of K also has to divide the order of G. So 12 has to divide this, and 20 also has to divide this. But then the LCM of 12 and 20 also has to divide the order. And their LCM, it turns out, is 60, which you can calculate, of course. So this is a necessary condition for such a G to exist. If there is one such G which is a finite cyclic group which has subgroups isomorphic to these two groups, then its order must be divisible by 60, and that's why it has to be at least 60. Now watch this. If we end up finding a cyclic group whose order is actually equal to 60, in which there exist subgroups isomorphic to these two things, then that will be the smallest subgroup, the smallest group, cyclic group, and that group is Z20. Note that I did not mean to say Z20, Z60, sorry. This is a cyclic group in which there exist subgroups of these two orders, 12 and 20. And in fact, from the classification of subgroups of a finite cyclic group, we know that, you see, let's just recall the classification. Say G is a finite cyclic group, and suppose the order of G is n. Then we know that not only the fact that the order of every subgroup of G has to divide n, but in fact, if K is a positive divisor of n, then there exists a subgroup of G whose order is K, and that is only one subgroup, only one such subgroup exists, it's unique. And since 12 and 20 both divide 60, so there are unique subgroups of Z60 having these orders, in which there are subgroups, say H prime and K prime, such that the order of H prime is 12 and the order of K prime is 20. But there is something else also. Another fact that we know about cyclic groups is that any of its subgroup is itself cyclic, since H prime and K prime are cyclic, being subgroups of Z60. So that's why H prime will be isomorphic to Z12 and K prime will be isomorphic to Z20. So that means Z60 qualifies to be such an example, and from this previous part we know that it's the smallest such. So this is the solution. So that means Z60 is our smallest cyclic group satisfying these conditions. Next, (24). Suppose that phi from Z20 to Z20 is an automorphism. And the image of 5 under phi is 5 itself. So 5 is a fixed point of the function phi. What are the possibilities for phi of x? What can phi of x possibly be if it has to satisfy these conditions? Okay, so we will start from this this hypothesis that is given. Okay, this implies what? Because we are in an additive group, we know that the binary operation here in this group is addition modulo 20, and phi is an automorphism. So phi is going to respect that binary operation. So phi of 5 is in fact phi of 1 plus phi of 1. Like that, we take 5 copies of phi of 1 and apply the operation on those. So that means 5 times phi of 1 is equal to 5. Now this is an ordinary equation in this group, but if you treat these things, these individual objects, as ordinary integers, then this equality will turn into congruence modulo 20. Which means that this implies it's just writing that same equation, same condition, but in the language of congruences. Congruent to 5 mod 20. And what does that mean? That just simply means that 20 divides 5 times phi of 1 minus 5. Let's just write that. That way it will be easier to understand if you are not very familiar with these modulo equations. 20 divides this, 5, and that implies, if you do this little cancellation, that just simply implies that 4 divides phi of 1 minus 1. or phi of 1 should be of this form: 4k plus 1 for some non-negative integer k. So this gives us an idea of what phi of 1 can possibly be, and from that we can guess what phi of x can possibly be. Alright, that's because once you know phi of 1, you actually already know phi of x because of this. See, phi of 5 is 5 times phi of 1, just like that phi of x is x times phi of 1. Alright, now recall a property of automorphisms, namely that you know that this 1 is a generator of this is the cyclic group after all, right, Z20, and 1 is a generator of this group whose order in the group is 20, okay, because modulo 20. And the property of phi is that it will map this generator again to a generator. That should be true. So we cannot just simply take any arbitrary 4k plus 1 to be a possibility. So let us see for which values of k we get generators of Z20 here. Thus, phi of 1 belongs to, let's just write all the possibilities first of all, and then we will figure out which one of them become generators. K can be taken as 0, so you get 1. Then k can be taken as 1, that gives you 5. Then next, 4 times 2 plus 1 is 9. 4 times 3 plus 1 is 13. 4 times 4 plus 1 is 17. And if we go beyond that, then we will get repetitions. That means these are the only possibilities. That's because these are the possible remainders in this situation when you divide an integer by the modulus 20. Modulo 20 you cannot go beyond, you can go, but you will get these things only. Now recall the condition for an integer to be a generator of this, and that condition is that the GCD, if k is your integer, do not confuse this k with this k, okay. Let me take something else, k prime. K prime is an integer. K prime will be a generator of Z20 if and only if k prime and 20 are relatively prime, that is their GCD is 1. In other words, there is no common factor between them, no common positive factor other than 1. So is that the case with the numbers here? 1 and 20 of course are relatively prime. 5 and 20 are not relatively prime because 5 divides 20. So the GCD of 5 and 20 is 5 itself. So this is ruled out. 9 is relatively prime to 20. 13 and 17, these are primes themselves, so they are relatively prime to 20. Not simply because they are primes, but they are primes which do not divide 20. So that's why the GCD is 1. So now we have to write accordingly, since phi of 1 has to be a generator of Z20, GCD of, in fact, let's just write the condition itself. GCD of phi of 1 and 20 has to be equal to 1. So, phi of 1 is not equal to 5. And should I write about the others? And the other possibilities what should I write? The other possibilities persist. That is, they don't go anywhere, just like 5 is gone. So these are the possibilities for phi of x. Phi of x is x or 9x or 11x or 17x. So we get actually the functions themselves. So these are what phi of x can be, can possibly be. That is the solution. And let's see one more. Identify a group G that has subgroups isomorphic to Zn for all positive integers n. I think a little ink is needed at this point. So your group should be such that it has a copy of Zn as a subgroup for every positive integer n. And in fact, a hint is given at the end of the text, and that hint says it all. For this kind of group, you have to look in the system of complex numbers. That is the hint. Let G be the group of all complex numbers of absolute value 1 under multiplication of complex numbers. We already know that this is a group, and this group can be pictured also in the complex plane. It is the unit circle, because those points precisely are the complex numbers that have absolute value 1. There are infinitely many. This is an infinite group, an abelian group, fine, but then this is an infinite group. in which there are many complex numbers that we already know. For example, 1, minus 1, I, minus I, these things are elements in this group, and the operation is complex multiplication. Okay, now let n be any positive integer consider the complex number omega. Omega, in fact, just to show that it depends on, and let me put a suffix. Oh, I do not have enough space to write it here. Let me write it there. Omega n, which is cos 2 pi over n plus I sine 2 pi over n. Then this set, should I name it something? Yeah, because I'm going to say something about this set now. Suppose, let me just call it Hn. 1 omega n square, and so on up to omega n to the power n minus 1. This set is a subset of G. We already know from simply from the form of this complex number and the fact that cos square theta plus sin square theta is equal to 1 for any real number theta, that omega n has absolute value 1. That means omega n is a complex number that belongs to G. So then, from properties of absolute value, all these powers of omega n also are complex numbers of absolute value 1 automatically. So Hn becomes a subset of G. But not just that, we also know that this Hn is a subgroup of G. Why? Because of this fact. Since the nth power of omega n is 1, and in fact the nth power of every element in Hn is 1, they are nth roots of unity, and these are all the nth roots of unity, precisely n number of them, right? And they are distinct. So these are properties from ordinary complex analysis. Using this fact, using this equation, you can easily prove that Hn is a subgroup of G. Also, we know that the order of Hn is n. Well, you can say that I can see that the order is n, but that is not necessary, no? If there are repetitions here, but we know that in fact these complex numbers are all distinct n complex numbers. So that's why the order of Hn is n. But from the way we have written the elements in Hn, you can clearly see that each element is an integral power of omega n. That means this group Hn is in fact a cyclic group of order n. Since Hn is a, and we know that up to isomorphism there is precisely one cyclic group of order n for every positive integer n, is a cyclic group, let's write this also, generated by omega n. So Hn is isomorphic to Zn, because this is also a cyclic group of order n. The operations are different, but that does not matter, they are isomorphic. So that's just it. You have found for every positive integer n a subgroup of G that is isomorphic to Zn. So essentially you have found a group G in which there is a subgroup isomorphic to Zn, means group theoretically Zn itself is a subgroup of G for every n. So that's how you have your example. And let me just end the video here itself. We are going to solve the other problems that come next in this list of problems in the next Gallian upload on groups. And tomorrow, as usual, we have our analysis upload. So see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.